My name is Craig Hogan, and I'm here representing Fermilab and the University of Chicago, where I'm a professor. I live in the park. I'm introducing an astronomer today as a speaker, and you might ask why I, an astronomer, work at Fermilab, and the answer is Fermilab doesn't just do big particle accelerators, but we also do experiments in what we call particle astrophysics, or the cosmic frontier, which is probing fundamental physics using the tools of astronomy, looking out into space. So one example is a thing that we've just built at Fermilab called the Dark Energy Camera. Is the heaviest camera ever made. It's about to be reassembled on a mountaintop in Chile to make a gigantic digital map of the southern sky with about 1 billion galaxies in it. That's to probe the Big Bang and things like that. Another set of experiments we do happen underground, deep underground. Instead of looking at the sky, we look for particles from outer space that penetrate the Earth and go into deep mines. And we build very sensitive detectors to look at that. Why are those interesting particles? Because we think they're called dark matter particles. They've never been detected, and we think they make up most of the mass of the universe. So that's another thing. We have several experiments like that. And then my favorite experiment, because it's with the one that I'm working on, is a machine we call the holometer. And that's it's designed to look at the fundamental nature of space and time, and to see whether all of this, this three-dimensional world we live in, is in some sense really a two-dimensional hologram, and we're looking for the two-dimensional graininess at very small scales. So that's what we're doing at Fermilab, and stay tuned. If you want to read more about it, a couple of weeks ago in The Economist, there was an article about dark energy and the Dark Energy Survey, and last month Scientific American had a feature cover story about the holometer, so that's about me. Today's speaker, Adam Frank, I've known for many years. He was a graduate student when I arrived at the University of Washington in Seattle, and he was so accomplished he didn't have to take any of my classes. we just today. But Adam works, and he's a very active researcher, one of the leaders in understanding the late stages of stellar evolution and hydrodynamic flows and all the wonderful things that stars do and gas outside stars. But today he's going to share with us a much broader picture of the universe, because he's really one of the great science expositors and explainers of science. And he's just come out with a new book, and he's going to share with us his ideas about time. So please welcome Professor Adam Frank. Thank
you. Can everyone hear me? We're good? Okay. So what I want to tell you about today is the last book, second book that I've written. It came out a little while ago, and it's about sort of my ongoing attempt to understand the relationship between culture and science. In this case, in the context of cosmology. So the title of the book is About Time, Cosmology and Culture at the Twilight of the Big Bang. I could have also called the book Timepocalypse, How Revolutions in Cosmology Mean the End of Time, yours in particular, or you could have called it Relax, the End is Near. And what I really want to talk to you about today is about the relationship between time as we experience it and time on the grandest scales that we can imagine, which is cosmology, the birth and death of the universe, okay? So the first question always with a book that the author certainly asks when you're into the 6th month of it, and the reader might want to ask, is why? Why write this book? And you may have noticed, if you follow this kind of thing, that suddenly there's been a lot of books, popular books on cosmology. A lot of popular books saying we're going beyond or before or pushing past the Big Bang. So there's Hawking has a new book out. Brian Greene has a new book out, which did very well. Even Roger Penrose, who's a bit more staid than those guys, has a book out, purporting to explain what happens before the Big Bang. And these books are full of crazy ideas in cosmology, string theory with extra dimensions and infinite numbers of universes different from our own. And then there's the holographic universe also, which is really a wild idea as well, that the universe is actually mapped on, the three-dimensional universe is really just a hologram itself. So the question I want to ask, though, about all this is really exciting stuff, but who cares, right? Other than cosmologists, right, and scientists, like Craig and myself, and people who kind of like to read books about it, does it matter for the rest of the culture, right? Does it really matter whether or not we're about to replace the Big Bang? And the answer I came up with was, yes, but not in the way necessarily that you'd think, right? So the way we usually think about cosmology and culture butting heads is religion, right? Science clearly, or cosmology clearly, asks questions that come up against theological issues, the origin of everything, whether the universe is infinite, will there be an ending, etc. And these clearly have ties to religion. And if you want an example of this, whoops, excuse me, I think I went the wrong direction. No, I just did something. There we go. Thank you. Okay, let me be careful with the mouse. These two images up here are interesting. This is the image up there is from a book about 400 years after the birth of Christ called Christian Topography. And it basically purports to explain the nature of the world, and it has the sun. The reason why the sun goes down every night is because it goes behind a giant mountain, right? And the whole universe is a big box, right? This after the Greek, the amazing cosmology of the Greeks with its epicycles, etc. So clearly, things can change in cosmology, and at times it can even become quite dangerous to have cosmological models that don't fit with the dominant religious thinking. Down here, actually, the second image is an image of, 1,000 years later or so, and the very ornate cosmology of Ptolemaic geocentric model, also which matched very well with the Christian ideas of the time. So, things can certainly develop, but then of course that was replaced by the geocentric model that we all know is true. The important point, though, is that religion was essentially the only place we saw cosmology and culture bouncing into each other. But I think there's a more important connection, and that would be time. And what I want to try and talk about today is the relationship between cosmological time and the human experience of time. That, I think, is the really important connection. Literally, the way we organize the day, the way we move through the day, is actually very closely connected to the cosmological vision that the culture you're born into has. And that's what I hope to give you some, or argue for that point. This is this image from the Renaissance, or just before the Renaissance, kind of illustrates this idea in general. Here you see, these were called like the wheel of time. You see a lot of these in the medieval period. And what you can see is these are all different things that happen during the year. You can see the threshing of the wheat, the planting of the wheat, etc., as the year goes around. And here are the astrological symbols. So people in these days knew that their daily life was tied to what happened in the sky in a very visceral way. That's an experience we've lost now, but it's always been there. And so the question is, what happens as you move from one time to the other? So what I want to first convince you of, to make this make sense, is that the time we live is an invention, okay? And so what do I mean by that? Let me ask you a simple question, which is, what time is it? Could somebody tell me what time it is? 12:30, I'm sorry, what was it? 12:34, thank you. 12:34, right? Which makes sense to everyone. No one's like, what? What do you mean 12:34, right? So, all these 7:36 p.m., 6:15 a.m. when you wake up, 10:22 p.m., 1:17 p.m. We're used to this. This makes sense to us. The question is, would it have made sense to anybody 1,000 years ago? What is 1:17 p.m.? What is the exact metering of moments that makes sense to all of us, right? But would it make sense to someone, a farm worker, so to speak, or in feudal Europe? And the answer, I think, is no. It wouldn't make any sense. It couldn't have made any sense because clocks didn't appear until 300 years, or until 1300, right? Minute hands don't appear until 400 years later. You can say, oh, well, there were sundials and everything. That's true, but most people had no contact with sundials. Right? It wasn't like, there's that old Flintstone thing where, Fred's wearing a sundial on his wrist. It wasn't like that. Sundials and water clocks were really the elite used them, and astronomers used them. But nobody else did. If you asked somebody 1,000 years ago what time it is, they'd say, after lunch. That's as good as it got. They didn't need anything more, and there was no technology for metering it. The culture didn't demand it, so there was no 1:17, right? So, the real meaning of 1:17, however, is something that you understand. Even though your great-great-great-great-great-great-great-grandmother couldn't have understood it, you feel it, right? You feel minutes pass. Why? Because you've been trained to feel it, right? Ever since you were born, from the day you were born, you've been trained to understand this kind of time logic. And that's my argument. Every culture has a time logic, right? You were taught it in school. When you went to school and you were told, hey, 8 a.m. is when we start. And if you're late, guess what? You're in trouble, right? And 9 a.m. is when we start math. And 10 a.m. is when we do history. So if you're enjoying math, stop doing it and start doing history, right? So that kind of time logic of parsing the day up into very exact and very well documented or, very well parceled moments is something we were trained from in the beginning. Certainly after school you get to work and time clocks, right? Your first job probably had a time clock on it. And then even in the realm of entertainment, one of the things I do in the book is I tracked the history of broadcast radio and the first radio networks, right? And what was important about radio networks is they taught everybody to live on radio network time, right? 7 p.m. was Amos and Andy time. And everybody across the country, in each time zone, right, because time zones had already been created, was ready to watch or listen to Amos and Andy at 7 o'clock. And 8 o'clock was Rudy Valley time. And the next day you all went in and you all talked about Rudy Valley, what happened the day before, which is exactly what we do today, right? Except for the fact that now it's changing again, right? Because of, and we can talk about this at the end, our digital technologies are making it such that, you can watch 30 Rock whenever you want to watch 30 Rock, right? You don't have to wait. Okay. So there are these time logics. Every culture has a time logic, and they change, right? And so my argument is that they've changed many times, and that they change in step with other things that are happening in culture, in particular, the vision of cosmology. Every culture needs a cosmology to justify itself. Whether you explicitly are into the Big Bang or not, I can probably go walk outside and ask anybody on the street, I'd say, how did the universe begin? They'd say, oh, something about the Big Bang. What is the universe made of? Electrons. Even if you didn't know very much about it, you were raised in it. Just like if I asked 1,000 years ago somebody what was the universe made of, they'd say angels and demons and God's universe of sin and mercy, etc. Right? It's just something you grow up with, even if you haven't studied it. All right. So if cosmology changes, then my argument is cultural time logic will change as well, or vice versa. The two are braided together. That's my metaphor. There's a braiding between culture and cosmology. I think I'm going to move this. That better? Good. Okay. So there's a braiding between these two, and that one changes, the other one changes. And so the punchline of this story would be cosmology is about to change. Right? We're about to move away from the dominant model of cosmology which we've had, which is the Big Bang. And I'll explain what I mean by that. It's not, we're going to talk about what I mean by the Big Bang. Really, it's the idea of the Big Bang as the moment of creation, okay? Not what came afterwards. But it's the idea that the Big Bang shows us that the universe had a beginning, okay? We're living at this very interesting moment which we could call the twilight of the Big Bang. The dominant cosmological model for the last 50 or so years is, on its last legs in some sense. So here's a timeline of times, right? I just want to show you the different times in which we've gone through this transition. So back 50,000 BCE, we were hunter-gatherers, and the way you move through the day, if you're, following the herds, is very different than if you're a farmer, right? The Neolithic Revolution, when suddenly we stopped moving around and developed villages and, planted and harvested, it's a very different kind of time logic, right? And that's very different than if you're living in a city, right? The urban revolutions of 4000 BCE, Egypt, Sumer, etc. This is a very different kind of time logic that you need. They're highly organized, highly segregated. And then, of course, once you get to the Renaissance and the invention of clocks, once again, a radical change in times. And then the Industrial Revolution, obviously, right? If you're working in a factory, your relationship to time, how your day is organized, how you're forced to go through the day is very different than any of these other ones. And of course, right now, we're in the midst of one, right? We're clearly in the middle of a revolution in time because of all of these devices. So let me give you two examples of this braiding of cosmology and culture. The first one is what we could call the Clockwork Universe. And so we go back to around 1100, 1200, 1300. Europe is emerging out of the Dark Ages, and the culture is becoming quite complex now. The cities are becoming quite complex as trade is beginning to grow again, and people are making money in new and different ways. And the cities needed ways to manage themselves, manage all the things that were happening. For example, when should the sheep shearers show up to work? When should the armorers show up for work? When do they get their breaks? When should the market open? When should the nobles be able to go to the market? When should the Jews be able to go to the market, right? And what their solution was, they had these what they called bells, market bells. A whole system of bells that would just ring different melodies, different times of the day. When those times were, they were using natural signals when the sun passed, what they thought was overhead. And then it became, impossible. The bells were going off all the time. You couldn't tell whether if you were a sheep shearer when you should stop work or go to work. And then around 1300, the first clock appears. Nobody knows who invented it, but probably was the monasteries. The clock was this idea of a toothed wheel with a weight hanging from it. And what it did was the wheel spun, releasing the gravitational energy, but in very precise units. The spinning of the wheel was broken up into very precise units, and you could build a clock out of that. And then these clocks swept through Europe. Within 50 years, every major city and major town had it. And the idea of the clock was there were no clock faces in the beginning. It was just the ringing of the bells only at predetermined, obviously every 60 minutes, predetermined times. So now you have this abstract system where the clock would strike 1, and that told you it was time for you to take a break. 60 minutes later, the clock would strike 2, and that would tell you something else. So all these market bells were replaced by this very abstract system. And eventually you get the clock faces, right? And the clock faces were a really radical idea, and they were great. And everybody who had one, this is like sort of having your town had to have a clock face. So if you look at etches of cities in those days, the artist would always put the clock face very prominent. It was like having your sports stadium, right? You have to make sure to show everybody. So this was a ye old beer garden clock face or something. It was named for somebody. So it was a big deal, right? Having these, yeah?
Is this about the time when the 24-hour day measure was established?
Well, no, the 24-hour, since the Babylonian times, that was when that had grown. And there's lots of arguments about why 24 hours, etc. But so, the original idea of breaking the day up in this way for Europe was called Italian time. Right? Some people, there were other ideas that floated around. But it sort of settled on this what had been known since the Babylonians, that you could break the day up into 24 seconds. And then there was also already, the argument about whether you should keep the clock going once the sun went down. Who cared if the sun went down? So, but that's actually a really good point, because before this, people lived on natural time signals. When the sun went down, you went to sleep, right? Candles were really expensive. So pretty much when the sun went down, that was it. That was the end of what you did. And you went to sleep. When the sun came up, you woke up. Now, as Lewis Mumford said, abstract time became the new medium of existence. One ate not upon feeling hungry, but when prompted by the clock. One slept not when one was tired, but when the clock sanctioned it. Right? It was this enormous transition to a different model, a different social organization of time, and it radically transformed culture in every way. When the courts met, when they gave their verdicts, when politicians met, how long university teaching was organized. So all of culture changed, and in its way, it changed cosmology. But then oops. No, sorry, which way do I go? No, don't worry. I got this. I'm good. I think I'm good. I pressed. Which is ironic, right? Yeah, it just doesn't. Here, how about this? Up. There we go. I think I turned it. I might have turned that off. Okay, so there we go. So in 1377, 70 years or so after the clock is introduced, Nicholas Erasme writes, he was a philosopher, natural philosopher, and he's writing about the motion of the planets through the heavens. This was still a time when there was, it was a geocentric model, but people already knew that there was this regularity, obviously, in the planetary motion. He says, this is similar to when a person has made a clock and sets it in motion, and then it moves by itself. Right? The idea of a clockwork universe suddenly appears, and it sweeps through natural philosophy and becomes a very potent metaphor for thinking about the universe, so much so that Newton really uses it in his thinking. Newton comes up with these laws of motion for what happens on Earth and what happens in the sky, and these laws of motion become kind of the metaphorical gears, in God's clockwork. And Newton uses this clockwork universe idea to build an entire foundation for thinking about the universe and thinking about cosmology, even, because the earliest ideas of mathematical cosmology you can kind of trace to Newton, where he thought about having all the stars arranged in the sky in a perfect lattice that would, where the gravitational pull of every star kind of canceled out every other star, so you could have an infinite universe that was perfectly stable. And you could write down the equations for this, right? He knew there were some problems with it, but it was the first shot at it. So the Clockwork Universe followed the introduction of clocks, okay? So let's look at another model of this. So I've given you one example. Let's look at another one. And this is Einstein and what happened with Einstein. So, as astronomers and physicists, we get this sort of idea that Einstein, after he got his PhD, went on, couldn't find a job as a professor, and took a job as the patent office. And that his time at the patent office, 8 years, was kind of like working at McDonald's. He's flipping burgers, and in the meantime, thinking about relativity and dreaming up relativity. But that's not really the truth. Right? That's not the patent office. What was Einstein doing at the patent office while he was coming up with the theory of relativity? He was working on his job they gave him, because I knew he was a smart guy, was to evaluate electromechanical time synchronization devices. What does that mean? If you have a giant factory that spans acres and you want all the clocks in it to be synchronized, right? How do you wire them all together? This was the kind of thing that Einstein was being asked to evaluate. He was being asked to evaluate ideas about keeping clocks, keeping time synchronized across space. What is relativity but a theory about time and space? So in many ways, the ideas that he was being asked to evaluate, this cultural movement to understanding space and time, informed what he was doing with relativity. And let me give you a very specific example of this. Trains, right? In the 1800s, train travel is now becoming, standard. And train travel was radical. You could travel at 30, 40, 50 miles an hour. Nobody had ever done that before. You couldn't do that on a horse, right? Not for very long, at least. And so, for example, with trains, it used to, in 1790, to get from Philadelphia to New York, took a day and a half on the Zephyr, right? It was the stagecoach, right? It was the fastest way of getting there. Day and a half. By 1880, you could do it in 3 hours. So what does that mean? Well, in 1780 or 1790, it didn't matter whether New York and Philadelphia were running on the same time, right? What does that mean? It means that, New York hires an astronomer to say, oh, that's noon, and that's how they set their clocks. Philadelphia hires another astronomer and says, that's noon, and they set their clocks. It doesn't matter whether they're synchronized. By 1890, it does matter, because if you're coming from Philadelphia to New York in 3 hours and you have a meeting at 4:30, you need to make sure that when you get into the Philadelphia train station and you set your watch and you're like, oh, okay, this is good, that it's synchronized with what was going on in New York in Grand Central Station. So synchronizing time across space was a dominant cultural issue that the culture was trying to figure out. Yes?
I don't think it was for the convenience of the passengers. I think it was for the convenience of the essential need of the railroads, because railroads had to run by clocks, so it was essential that people using the same track coming different directions do what.
Right, not slam into each other. Right. Well, no, you're right. Actually, the time zones, what's interesting in the development of time zones, when it was codified here in 1883 with Chicago, it was done not by some government bureau, it was the railroads. The railroads determined the introduction of time zones into America. So you're right, it wasn't for people, it was for commerce. It was the engines of commerce. So the culture needed to change its time logic. Trains were the reason why the culture needed to change its time logic. Telegraphs were another example. The world was being strung with telegraphs, cables, and telegraphs provided near instantaneous communication. Suddenly New York and Paris could, talk to each other as if they were, right next to each other. Now this was a radical idea in and of itself, a simultaneous now across wide distances, but it was for another reason, right? The reason why telegraph cables were going all around the world is you needed measurements of time to determine longitude, right? If you want to know where you are on the planet, to really do it accurately, you need a simultaneous measurement of what the time it is where you are and the time it is against some reference point, like Greenwich, England. And now people were doing that. This was important for a lot of reasons, but particularly this was the age of empire, right? And if you wanted to know whether your copper mine was on this side of your African colony or that side of the African colony, you needed to know exactly what the map location was. So for reasons of geopolitical interest, questions of time and space and simultaneity were fundamental, right? And what is Einstein doing in the theory of relativity? He's developing a theory of time and space and simultaneity. right? So he wasn't doing it for, for cultural reasons, but he was immersed in a culture that was the dominant question, the dominant technological question. So Einstein's theory of special relativity, and then the theory of general relativity, which emerged from this time, really brought forward a fundamentally new vision of space and time. And what was that vision? It was a vision that space and time, first of all, were unified, right? Which already the trains were teaching us on some level, right? How far away is Buffalo from Rochester? Oh, it's about 60 minutes, right? It's not 60 miles, it's 60 minutes, because the way I travel, I can get there in 60 minutes. Before that, it was a day and a half or so, or something even longer, depending on if you had to walk or not, right? So he taught us that space and time were merged in a fundamental way, not just in this sort of how fast can I travel way, in a fundamental way. And he also taught us that space and time were flexible. They weren't emptiness. Space wasn't emptiness. It was a flexible fabric that could be bent and distorted and stretched. And what Einstein found was the relationship between the two was that matter would tell space how to curve. Matter distorts space-time actually. And space tells matter how to move. So he found a relationship between matter/energy and the shape of space-time. And the reason why that's important for us is that this is essentially, so this is this nice image, there's a classical picture of the Earth distorting space-time, and there's a satellite being forced to move in the way that space-time is curved, right? That's why there are orbits, okay? But the important thing for us is that this new theory allowed the first truly global vision of the universe. You can't do a cosmology unless you have some way of describing all of space-time at once. And that's what this theory provided. Einstein gave us a theory that could describe the entire universe in a single equation. So for example, right, when we think about cosmology, what's the question that always comes up with space? Is there an edge, right? And it's hard to think about cosmology without sort of asking that question. Einstein gave us ways to answer questions about whether the universe was truly infinite or whether it could be bounded. This is this classic example of if space-time were like the surface of a sphere, right? So you have these little ants walking on the surface of a sphere. If space-time were warped on itself, back on itself, in this spherical shape, then what it would mean is I could take my spaceship and point in that direction and keep heading out straight, and eventually I'd come back from there, right? And so Einstein allowed us to see that space could be bent and warped and curved like the surface of a sphere, okay? So in that metaphor, then three-dimensional space is actually a three-dimensional hypersphere, right? It can warp back on itself. So there was an example of Einstein giving us a way of dealing with issues that had always been around in cosmology, but now being able to ask different kinds of questions about them. And the important thing to remember is that the Big Bang is essentially a general relativistic cosmology, right? You couldn't have the Big Bang without general relativity. And what I'm trying to show also is that you couldn't have general relativity without what was happening in culture at the time. Oh, okay. Excuse me. Sound is just... technology. All right, hopefully stand still. Sorry, I'm from New Jersey, man. You can't keep me. I'm talking with my hands. The Big Bang, it was a huge. Okay, so where are we now? Well, we're at the precipice. We're at the twilight of the Big Bang. And so what I'd like to do is maybe spend the next 20 minutes or so talking about the Big Bang and its alternatives. Okay, so that'll be sort of where we're heading. But first, I want to briefly go through what the Big Bang is itself, right? If we're going to talk about what's going on beyond the Big Bang, we got to talk about the Big Bang. So the Big Bang has got this story, right? That the universe began as a single compressed point that contained all space, time, matter, energy, and dimension, right? So there's no outside. That's one of the things that Einstein gives us. There's no outside. All of reality, all of existence is this point. The point explodes, expands, right? Doesn't expand into anything. Its expansion is the expansion of reality itself. And it's very hot in the beginning, and as it cools, the matter in it congeals and forms all the structure that we see today. So, here's this sort of standard image. So that is the gold is the fabric of reality. You can think of those dots as galaxies, and you can see as the fabric of reality stretches, every point is pulled away from every other point. So that's the expansion that we see in the universe, okay? Here's a timeline of the Big Bang. You start off somewhere here. As space expands, it cools. So originally things are so hot and dense, they're very much in Craig's regime, where, it's all particle physics, and you have to understand sort of what are the particle physics interactions. But it's very much a very super hot particle soup in the beginning. Let me see if this thing is still working. Yeah, there we go. And then as time goes on, there's a very special time here, which we'll talk about, where fossil photons, which become fossils, are released. This is what's called the cosmic microwave background. Photons are released, which are able to travel unimpeded all the way up to us now. But as time goes on, what you see is eventually structure starts to form. Galaxies, clusters of galaxies, and as time goes on, things continue to evolve until we get to this point now, 13.7 billion years after this. And it's a great story. The Big Bang is a great story. But it's important to understand that it was never a story of what happened at t equals 0. It was always a theory of after. The Big Bang is a theory of after the Big Bang. And it is brilliant and beautiful. And we believe it because we have some excellent evidence. So I just want to talk very quickly. Why do we believe the Big Bang? We've got 3 pillars of evidence that tell us that this theory is true. The first is the expansion of the universe. We look out at galaxies, we see them all expanding away from each other. The second is the primordial abundance of elements. If the universe is very hot and dense in the first minute, it's like the center of a star. The whole universe was like the center of a star. And you could fuse hydrogen into helium. Hydrogen atoms were smashing into each other and fusing and forming helium. So we go out and measure how much helium there is. And if it concords with the experimental, or with the theory, then we believe the theory. And the experimental prediction and the theory match beautifully. The last is the discovery of the cosmic microwave background radiation. You can ask me afterwards, if you want, where it came from, but it's basically these photons, this light that was released about 300,000 years after the Big Bang, and then basically the universe was transparent to them ever after. And so when we discovered this in 1964, it was the most important discovery in cosmology at the time. It was actually discovered in New Jersey in 1964. So New Jersey was responsible for discovering the Big Bang. As a New Jerseyan, I think that's very important. So we have these 3 amazing pillars of the Big Bang. And if you have any other theory, you need to be able to explain these 3 pieces of evidence. And that's why the Big Bang has lasted for so long. And it became the classic dominant model. It became the model of cosmology. Then it got married to another standard model, which is what's called the standard model of particle physics, which basically is what has come out of Fermilab and other, the Large Hadron Collider, things like that. It's basically a theory of matter, right? And what the standard model tells us is that there's only a few kinds of matter, quarks and what are called leptons. The electron's an example of a lepton. And there's only 4 forces. That's amazing. There's gravity. There's the electromagnetism, there's the strong nuclear force, right, which keeps atoms bound together, nuclei bound together, and there's the weak nuclear force, which I've never been sure what it does, right, but it's there, what can I say? So you only have 4 ways in which matter can interact with other matter, and this standard model of particle physics pretty much explained everything. There were lots of sort of free parameters in it that you could tweak, but it certainly explained everything we were seeing in nature. And so you can couple that with cosmology and general relativity, and you could track from right after the Big Bang onward, again, right after the Big Bang, all the transformations that matter went through. So the standard model of particle physics and the standard model of cosmology, the Big Bang, were a beautiful marriage. But it was not a marriage made in heaven. Because eventually, by the early 1980s, paradoxes had started to show up in the Big Bang, okay? And I'm not going to go into these in detail. I'll just give you one example of them. One thing is that people really understood from their descriptions of matter was that there ought to be monopoles, magnetic monopoles. What do I mean by that? When you take a magnet, right, it's got a north pole and a south pole. You break it in half, each piece has a north pole and a south pole. Basic physics said at some point there ought to be just north poles and just south poles. Just like with electricity, you've got plus charges and minus charges. Nobody's ever seen these monopoles. So that was a huge question for the particle physics part. Why were there no monopoles? From the expansion of the universe part, there were also big questions. There were paradoxes that had arisen. I won't go into them. You can ask me about them later. The point was the Big Bang flaws had started to show up in the Big Bang. And in order to get over them, people came up with this new idea, which they grafted on to the Big Bang. And it was something called inflation. Okay, so here I'm listing a couple of different things that were how inflation solved the problem. I don't have time for this now. What I want to show you is just what inflation did. And what was really interesting, what inflation did is it didn't talk about the whole Big Bang. It talked about just a piece of the Big Bang, right? So you can imagine this is the universe after the Big Bang. This is time. And what inflation did is it said, you know what, there's a little tiny sliver of the universe which, you know, is expanding along happily, and then it goes through this wild period of hyper expansion. It's like expansion on steroids. This little tiny sliver of reality goes through at around 10 to the minus 33 of a second after the Big Bang. So that's one thing. This happens really early, right? Now, 10 to the minus 33, that's like such a sliver of time, it's almost, you know, impossible to wrap your mind around. But the idea is at this very early moment, so this is sort of the radius or the size of the universe, you go through this unbelievable increase in the size of the universe, which then stops and it settles down to the normal expansion we see today. So this idea of inflation solved, for example, the monopole problem. Why? Because it said, yeah, you know what? There were a lot of monopoles around here, but when the universe expanded this way, they got diluted. So that your odds now of ever seeing a monopole are basically zilch. So they're there, you know, in the numbers that we think they should have been created early on, but this inflation diluted everything, right? So that was one way you solved the paradox with having this early period of super duper expansion, okay? So inflation, now cosmology became not Big Bang theory, but inflationary Big Bang theory. And it did a great job. It explained the cosmic microwave background radiation. This is a picture mapped onto the whole sky of these fossil radiation. And you see it's got these little dots here, right? Blue, red. The red is slightly denser and slightly colder. The blue is slightly hotter and slightly less dense. Right? So even early on in the beginning of the universe, you could already see, our data already shows us that the universe was uneven. It had little ripples in it. Well, why does that matter? Because here's a picture of the universe now. This is billions of light years, right? This is a map. These are all galaxies. And what you see is the galaxies are not uniformly distributed in space. You have these giant holes that are, you know, billions of light years across, or hundreds of millions of light years across. And then you have lots of galaxies in these filaments and sheets, right? So what we figured out, what inflation gave us, is a way to understand where these seeds came from and allowed us to see how these seeds actually propagated into the structures we see today. You and I are already imprinted on these tiny fluctuations at the beginning of the universe, okay? So inflation, that was the triumph of inflation. It gave us a way of understanding that. It gave us a way of getting over the problems with Big Bang cosmology. But there was a tragedy of inflation too. And the most important part was these new discoveries. The first was the discovery of dark matter, the idea that there's a whole lot of matter out there that doesn't participate in any of those forces except for gravity. Remember I said there are 4 forces? Dark matter, we only see it because of its gravitational effect on the stuff we can't see, okay? So dark matter was a new discovery, and it wasn't necessarily a problem, but in 1999, dark energy, we also discovered that there was this extra energy in the universe that was, right now, we're not just expanding, we're actually accelerating. The expansion of the universe is actually getting faster and faster. And nobody really predicted this, right? Nobody predicted this, and certainly not at the degree that we see it, okay? This came as a complete surprise. Now, why was this a problem for inflation? Some people may disagree with me in saying this, but, you know, inflation, the whole idea of inflation is that early on, the universe goes through this wild period of expansion, which is really an acceleration. The universe accelerated in its expansion and then slowed down. Now we're saying, oh, guess what? It's also accelerating now. And the acceleration of inflation and the acceleration that we're seeing now are totally disconnected, right? If inflation was really, really, really super duper theory, it would have predicted that there was going to be this dark energy, right? I mean, it would have said like, hey, you should expect this, it's coming out of it. Yeah.
I asked once whether the universe was, after the inflation, was bigger or smaller than the Ford pickup truck. And the answer was it was quite a bit smaller.
I think it was the size of a grapefruit, I think.
Basically, it's going from the size of an atom to the size of a grapefruit. Why not? You get all those monopoles in a grapefruit?
Well, it's actually the inflation of the entire, because what happened with us is our part of the universe stopped inflating, and the rest of the universe was still inflating. And so that's really where so there's still, as we'll talk about, there's still more of the universe that's inflating out there. So that's really where things get carried across over the light horizon, so they can't be seen anymore. So it's all of space that's actually involved not all of space drops out of inflation at the same time. Okay? And so that's really where the dilution occurs. Okay, so when I say the tragedy of inflation, I mean, people love inflation. It does really great things. It's whether or not really, it never answered also the question of what happened at the Big Bang, right? Inflation was still a theory of after the Big Bang, not a theory of the Big Bang itself, of creation itself. So that's in some sense why, you know, there was still kind of, it didn't answer the fundamental question, which was why there was a Big Bang. And also it requires what we might call fine-tuning. To get the theory to work, to get our visible universe, you have to have our part of the universe drop out of inflation, out of being inflated at just the right moment, okay? And so, you know, you have to kind of tweak the knobs and the dials on the theory in order to get it to do that. And that also bothers, you know, some scientists as well. So the point is that now here we are, you know, 10 years into the new millennium, and where is cosmology now? We've had inflationary cosmology since sort of 1980. It does wonderful things, but it still doesn't answer the fundamental question, and everybody got taken by surprise by dark energy, okay? So what I want to review now are some of the new ideas. I'll spend the last 10 minutes on this, some very quickly. Some of the new ideas that are out there sort of trying to deal with, you know, where do we go from here? But I don't want to lose contact with the culture again, because cosmology and culture circa 1990 and 2010, as we're realizing we can push beyond the Big Bang, is being driven by the same forces in many ways that have driven culture, right? So I don't need to convince you that the internet, GPS, social networking, et cetera, is radically altering your time, right? Many of us are old enough to remember, you know, before we had cell phones and how different it is to have a cell phone. And just the act of walking down the street and talking on your cell phone is a radical re-envisioning of what it means to do with your time, right? It used to be that you had to walk from point A to point D. You just had to think your thoughts, right? There's nothing else to do. Now it's like, of course, oh, take out your cell phone, call somebody, because we don't know what else to do with our time. Right? These same technologies have radically transformed cosmology and science. And the amazing thing about this is that, where was the first web browser? It was developed actually here, right? It was developed in at University of Illinois at, what is it, the National Supercomputing Center for Astronomy. I forgot the acronym. But basically, you know, Mosaic was developed by astronomers to be able to share data, right? The HyperNet, or the hyperlink protocols for the internet were developed at CERN, right, to allow particle physicists to share data. So a lot of these technologies which have reshaped our life started as ways of trying to understand cosmology. And it's, you know, cosmologists, you would not be able to do cosmology today, these giant experiments, without scientists' version of social networking, being able to share data and share, you know, collaborative, paper writing across the internet. You wouldn't be able to take data on these enormous scales, like what happens at Fermilab, without these machines. So in many ways, what pushed us to the edge of now being able to, you know, that both data and theory has been this ability to, through these machines, to access the universe in different ways, ask questions of the universe in different ways. And these technologies are the same ones that are transforming time in our own lives. So again, they're, you know, this idea of cosmic time and cultural time are very coupled. They're even coupled now. Let me briefly say, one of the main reasons why we're pushing beyond, before, et cetera, the Big Bang is because we're at least getting some hints about quantum gravity, theories of quantum gravity. I told you there were 4 forces. 3 of them are completely described by quantum mechanics, which is the theory of the very small. One of them, gravity, is described by a theory that really can't, it's very hard to make it quantum mechanical. By quantum, I mean discrete. We know that the universe on the smallest scales breaks up into sand, right? It breaks up into chunks. That's what quantum means, chunks, packages. So we know that fundamentally, on the smallest scales, the universe becomes discrete. It comes in packages. Energy comes in packages. Angular momentum, the way things spin, comes in packages. You know, it's like I can ride, it would be like riding my bike. I could only ride my bike at 10 miles an hour, 15 miles an hour, and 20 miles an hour, nothing in between. That's what quantization means. On our scales, that's crazy. I can ride my bike at any speed I want. On the quantum scale, on the atomic scale, nature always breaks, is broken up into these chunks. Gravity, we could never make work that way. Okay? And so we've been trying for years to make quantum, or to come up with a theory of gravity that describes it on the space-time on this smallest scales. And of course you need that for the Big Bang. On the Big Bang, the entire universe is packed into a single geometric point. You better be able to describe gravity on those smallest scales, right? So this resisted everybody for the last 50 years, but now people think they're making some inroads on it. They don't know. There's a lot of argument about which inroad is the best, but they are making some progress. So string theory, etc., all of those theories, loop quantum gravity, purport to get us to time scales like 10 to the minus 44 of a second, or length scales like 10 to the minus 35 of a meter. All of these scales at which we believe gravity and space-time have to become quantum phenomena. So that's why this transition is beginning to occur now, to thinking before the Big Bang. Here's just an imaginative picture of quantum space-time. Literally, it would be like you'd have a chunk of space and time and nothing, and another chunk of space and time and nothing. People sometimes talk about foamy space-time, which I think is a great metaphor. All right, so very briefly, the alternatives now to the Big Bang. Well, one alternative is that you don't have the universe being created, you have cycles, right? Universe expands, it slows down, and then it contracts, goes through a big crunch, ba-boom, it goes through a big bang, back and forth forever, eternity, right? People love this idea. It's a logical, it's a logical alternative. You find it in, the Vedic myths of the Hindus, right? So this idea, certainly in the old, with using classical general relativity, classical Einsteinian ideas, people tried this, but it didn't work. It is for a bunch of different reasons. If you try and make a cyclic universe work in a non-quantum gravity model, it fails, right? But now, along comes something like string theory, right? String theory says the universe is not made out of point particles, it's actually made of tiny loops of vibrating string, okay? And, it's a beautiful idea, and one of the things that comes out of it is that in order to make it work, the physicists have to say, yeah, well, there's not 3 dimensions, there's 7, okay? So you guys are all used to the 3 dimensions. I can walk this way, I can walk that way, I can jump up and down, right? Those are the 3 dimensions we experience. String theory says, you know what, there's got to be more. There's got to be extra dimensions that we can't experience. So there's various ways they deal with that. Sometimes they can curl the dimensions up so that we don't experience them. But people took this idea seriously and said, you know what, maybe our 3-dimensional universe is embedded in a higher dimensional bulk. That there's more space out there, even if we can't experience it. And maybe there's our universe, which is like a sheet in this higher dimensional reality, and maybe there's another universe, right, that is also a 3-dimensional sheet in this higher dimensional universe, and if they ever collide, boom, that's the Big Bang, right? It's the collision between these brains, as they call them, membranes, right? This is a higher dimensional analog of a membrane. If they collide, that becomes the Big Bang. And then maybe they collide and bounce apart, but there's forces between them, and it draws them back together. And that could go on forever, these universes banging into each other again and again. And that seems to work theoretically. Right? There's still a lot of debate about it. It's not been proven by any stretch of the imagination, but it's a theoretical idea that seems to work. You can get an oscillating universe, not with just our universe expanding and contracting, but having another universe. And the expansion and contraction is between the space between the 2 universes. Okay? So using ideas from string theory, people have proposed this. It's a new way of thinking about the Big Bang that does away with the Big Bang. There's not one Big Bang, there's always been. There's been many of them in this cycle. Another possibility comes out of actually inflation, right? Remember, inflation was the idea that you had a piece of the universe that inflated and then dropped out of inflation to become the universe we see. Okay, what about the rest of the universe, right? What about the rest of the universe? Well, if people quickly realized that the rest of the universe might be going through its own periods of inflation and dropping out, and instead of one universe, you end up with a multiverse. You constantly get these pocket universes emerging out of the background of space, pieces that inflate and then drop out, and each different one has different laws, right? So you have a multitude of universes with a multitude of different physical laws, and this is what they call the multiverse. It's a very, very popular idea, and you can do all kinds of things with it, and people talk about eternal inflation now. So you don't even need a Big Bang anymore, right? Because you've always been getting these pocket universes emerging, right? Expand, some of them expand forever, some of them collapse back on themselves, but they've always been there, and they always will be there, and they're always expanding, and or they're always being born. Now, one reason why people like the multiverse is that there's always been this problem with the standard model of particle physics, that it has a lot of knobs and dials on it, right? So this idea of quarks and electrons and the forces, in order to make it work, you have to go out and make measurements, right? And there's about 20 numbers that you've got to put into the theory in order to make it work. The problem with it is if those numbers, if you change them even a little bit, if you make electromagnetism just a little bit stronger, if you make gravity just a little bit weaker, life never forms. And when I say a little bit, I mean like a little bit. 1 part in a billion, you change electromagnetism, and then biomolecules can't form. Change gravity 1 part in a billion, and stars, they burn out way before planets could ever form and life could form. So there's this problem of fine tuning, they call it. And of course, the intelligent design people love this. They're like, hey, God turned the dials, and that's why, we live in the universe we live in. Physicists, you can imagine, are not really happy with that idea. So what they like about the multiverse is it gives them a way of explaining this. There are infinite numbers of universes. They all have different physics, and of course, we ended up in the one where we could end up in, right? We ended up in the one that just happens to have the right laws, right? The other universes are sterile. Many of the other universes are sterile. So it deals with the problem of fine-tuning, and that's why people like it. Our universe does seem ridiculously fine-tuned for life, but it's not a problem because there's lots of universes that are not ridiculously fine-tuned for life, right? So, and you can even say, oh, let's do the statistics over universes. And if we want to imagine that, well, we can't live in a special universe, so our properties must be the average properties of the universe. You can even start thinking about statistics over different universes. Now, what I want to make, before we go any further, I want to make very clear that this idea, like string theory, the multiverse, is very popular among some cosmologists and particle physicists, not all by any stretch of the imagination. And it's very popular in the popular media, right? But the irony is, it's not popular with the rest of physicists, right? If I went through my department and asked how many people believe string theory or the multiverse is true, most of them would be like, get out of here, that's crazy. Now, why? Why are they kind of skeptical if there seems to be so much buzz about the multiverse? And the answer is there's not a single itty-bitty tiny smackerel of evidence for any of these ideas. As wild as they are, as much press attention as they get, there's just no data, right? Now, I'm not saying these ideas are wrong. I'm just saying that, we are still in a period of the Wild West. That's why I sort of love what Craig is doing, because they're actually looking for data. They're going to get some information that will help us sort through sort of all this pile of ideas. Now, there are some people who want to go even more radical. People like Lee Smolin, et cetera, and a colleague of his who's a philosopher, Roberto Unger. And they say, these multiverse and the extra dimensions, they're allegories, they're fictions. The job of physics is not to describe possible universes, it's to describe this universe. And I sort of like some of the thinking that they've done on this. As one of the quotes that Roberto Unger gave me is that a scientist should love their riddles, not sweep them away, okay? So I'm a little bit prone to this perspective, but it may very well be that string theory or the multiverse does get some data that supports it. In the meantime, lots of ideas are on the table. There's even really radical ideas like Julian Barber, who came up with these, who said the solution to the problem of the Big Bang is really the problem of time. And he said time itself doesn't exist. There is no time. There is no change. For him, the universe is made out of a bunch of discrete, ever-present, eternal nows. So this moment and the next moment exist separately and independently. It's like the pages, it's like a book. If you took a novel and ripped all the pages out of the book and just threw them on the floor, each page is independent, right? Each page is a page by itself. It exists in the universe by itself. I can take all those pages and organize them in one particular way where it seems like there's a nice story, but that's just, that's an accident, or that's the structure of the physics in what he would call Platonia. But the pages, the nows, are separate. So if you want to understand this viscerally, I love this quote, the cat that jumps is not the cat that lands, right? They're separate moments. They exist separately. There is no flow of time. That is clearly a radical idea. But, it's sort of where we're at. All ideas are kind of on the table. So I want to end now. So I've just given you, a bunch of possible alternatives. There's a lot more out there. In the book, I discuss more. But I want to end with a couple of morals, right? Now, books on cosmology don't usually have morals at the end, like a bad Saturday morning cartoon, But Davy, you should love your friends, right? So this book does have a moral, though, and my moral are two parts. There's nothing God-given or physics-given about the time that we live in, right? The social organization of time. Modern time was an invention. It was a social construction for historical and social reasons, right? And in particular, modern time has a very peculiar logic or a very peculiar value, and it is efficiency. Hyper-efficiency. You can go back to the work of Taylor in the 1890s. He was the guy who, with the stopwatch, who was looking at every movement you made and clicking, watching with a stopwatch and saying, you could do that in 3 seconds shorter. When you open that drawer, that took 1.6 seconds, you could probably do that in 1 second, right? That's that management, that idea that, you can do more in less time. That's hyper-efficiency. And it's clearly what our culture is about, right? The problem is, and it didn't have to be this way, but it ended up this way, that hyper-efficiency led to hyper-consumption, right? Hyper-consumerism. And that's what led to the mess we're in, right? One way or the other, we are definitely facing major issues of resource depletion, right? We're eating up the forests, we're eating up all of the oil we have, one way or the other, we have this problem that our sort of time logic leads us to try and do the most we can in the shortest amount of time, and that has led us to consume the most in the shortest amount of time. So there is this moral of understanding that this time that we have is not the only way to organize ourselves, right? And it can change, and most likely it's gonna have to change, right? It's very hard to imagine that we're gonna be doing what we're doing now for 100 years, right? That some way, either a great subtraction from what we're doing, or maybe through some new technologies, a great addition, this culture can't last. It's being strained by just the consumption of resources that it uses. It's a finite planet. You're only going to be able to do this for so long, right? So one way or another, this culture will probably have to change. Not a big deal, because it's changed lots of times in the past, right? 100 years ago, this isn't what the world looked like, right? The assembly of this network of roads and telegraph cables and everything, that happened very quickly, right? Your great-great-great-great-great-grandfather never would have experienced this kind of world that we live in. Now, if cosmology is about to change, which I've just been arguing for, then likely, if history is any guide, culture is about to change as well, right? So, and that cultural time is about to change as well. Which kind of leads me to the second moral of the story, which is about the nature of science and truth, which is something, I think about a lot, right? So every culture needs a cosmology to justify itself. It's the background. It's the, it's why the culture thinks it's right in the way that it's organized the universe, right? Now, every culture, or every cosmology reflects that culture, and particularly reflects what I would call the material engagement. It reflects technology, right? Cosmology you can do cosmology based on, the way you do it is reflected on what you do with stuff, right? Can you build a big telescope? Or are you observing with naked eye, right? Are you using ropes and pulleys, or are you using electrical cables? Technology determines how you organize your culture, and it determines how you can look at the universe as a whole, right? So cosmology and technology are very closely aligned, and there's a boring conclusion from this, which is just that, technology gives you new data, you get a bigger telescope, you get a new way to see the universe. But there's a more interesting way of thinking about this and about the relationship between science and truth, which is that your dominant technology shapes and constrains your imagination, right? It shapes each culture's cosmological storytelling, right? So here's the obvious example of that, the Clockwork Universe. Suddenly clocks are everywhere. The universe is a clock, right? Now we're starting to think very much about the universe as an information processing device, right? You see this a lot. The universe as a mechanism for dealing with information. Should this be a surprise? Our dominant technology is information processing, right? Now you can say, oh, that just means we're all stupid and we're just, we can't help but think with it whatever we have. So we're totally wrong. No, it just means that as we move through time and in our investigations of the universe, these technologies, sort of give us the range of options or allow us to imagine a range of options that changes as the technology changes. So rather than thinking about science as this search for some objective, pure truth, this truth about, this direct contact with the external, independent, objective reality, for me at least, it makes science more of a dialogue with the world, right? And in the dialogue, you can't take one person out of it. If you've got two people talking, you can't take one out. It's not dialogue anymore. So it puts us back into the equation in a way that I find interesting, right? So in many ways for me, the search, what cosmology becomes is like the parable of the blind philosophers examining an elephant, right? The one guy feels the tail and says, oh, an elephant's like a snake. Another guy feels the feet and says, an elephant's like a tree, right, et cetera, et cetera. That is humanity's progress through its history, right? And that's how humanity's progress through its culture and cosmology, is that we are, it's like the universe is an infinitely faceted diamond, and we keep getting views of different facets. And to me, that's much more interesting than just saying there's a pure objective world out there and we have absolute access to it. It's, for me, it'll always be this dialogue, okay? And that's what, to me, that makes the whole thing a little bit more interesting. So let me leave you with this quote from Peter Galison, who I really, really enjoy. He was the one who wrote the excellent book on Einstein and his time in the patent office. Forging back earlier than the 18th century still does not shake timepieces loose from the cultures in which they were built. Sand clocks and church clocks carried much beside the assignment of time. They conveyed different overlapping authorities of God, of the feudal lord, of the memory of mortality. There's simply no getting behind the cultural to show some primordial moment in which time was nothing but sand shadow or mechanical pointer. So I thank you for your time. Questions? Yes.
I've read that the universe is expanding at a linear rate, 70 kilometers per second per light years. You said it was expanding faster and faster.
Right. What it means is that at different times in the universe's history, that rate has been changing, right? And so what happened was the way the acceleration was discovered is that people actually expected that the universe would be decelerating. They thought after the Big Bang, basically the Big Bang was the impulse that drove the universe into expansion, and then that all the gravity of all the matter would be pulling on everything else so that we would actually, over time, see the rate of expansion changing, slowing down. So what it means is, no matter what expansion you see right now, if I could look into the past or look into the future, I would actually see a different rate of expansion. And so what we found now, when we went out and looked, is we find that the universe is actually accelerating. That's now expanding faster than it was in the past. And that was the huge surprise. Yeah?
Okay, I'm trying to put my mind around everything that you said, which is a lot.
Right.
So here's what I get. That our culture strongly influences how we approach science.
Yes.
Okay, so then there was a huge moment in history where our culture was going through the introduction to time, the concept of time. And so that influenced how we looked at science. And so during that period, we came up with the theory of the Big Bang. And then I hear us discussing it now, and it seems like the Big Bang involves the rate of expansion of the universe, or
Right.
time.
Right.
And whether it's speeding up or what. And so that sounds like time. But then I hear you say that we're about to make a transition from a time-based, time-centric view of science to something else, maybe an information processing view of science. And so then maybe the theory of the Big Bang will yield to some other information-based theory. And we'll start looking at the origin of the universe as something else.
Yes. I think overall, I would, qualify some of what you said. So let me perhaps say, try and take what you said and sort of add to it or clarify.
I thought I was taking what you said.
Yeah, right. So I think overall you got it. That was pretty good, right? And I can't say which direction which direction's going to go now. I mean, I cannot. People often say, well, what's going to come next in cosmology, and what's going to come next for culture, right? Culture. Remember, what I'm saying is that every culture has its own time logic, its own way of organizing the day, right? Organizing our movement through the day. Like, the day is what we get, right? I mean, those are the boundary conditions, so to speak. The sun rises, the sun sets, we all live, 80, 90 years, hopefully, right? But it's how we organize ourselves, how the culture organizes itself. That's the changing time logics. And those are very much shaped by material engagement, how we, what we do with the stuff we find in the world. And that shapes our cosmological vision, right? That shapes how we look at the universe and the stories we tell about the universe, either through myth or through science. So that's sort of what I'm saying changes as we go along. Where we are right now is that we've come to the end, I think, of the cultural time logic because of this issues of resource depletion and that one way or another we're going to be forced to sort of shift the way we organize the day, organize the year, organize commerce because of these issues. And already we can see ourselves beginning to shift our understanding of cosmology. The information processing is one way it could go. It could go in a completely different direction, which is that, let's say we don't manage to make this transition over the next 100 years, right? And we suddenly have a lot less energy to deal with, right? It may be that cosmology, I wouldn't want to call it a step backwards, but we can't build these giant machines anymore to probe the universe. What happens to cosmology then? It'll change, right? If suddenly there is no next Hubble Space Telescope, there is no next Large Hadron Collider because we're too poor, so to speak, or we don't have the energy to marshal our time to build things like that, then you know what? That next culture is going to have a different cosmology. So it doesn't have to be this addition of like, ooh, we're flying in spaceships, in jets and space cars. It could be a dark age. That has happened, also as well. So all I'm really trying to point out is that there are these changes in cultural time logic, and you could say cosmological time logics, and that they're wedded together, and that we're in a period of change again. Is that okay? Okay. Yes.
Would it take, for example, the discovery of, say, an extrasolar system object older than the known age of the universe to prove the age of a multiverse or a parallel universe? Let's say space rocks, say, 16 billion years old.
Well, you know, that's a really good question. What would it take to prove the existence of a multiverse, right? And this is an interesting question because clearly, you know, if 50 years from now we still don't have any evidence for the existence of a multiverse, that theory is just gonna, you know, there'll still be maybe a bunch of people working with it, but it's gonna go away because it's just nobody, you know, without data, it can't. These theories are not gonna live very long. And this has been sort of the argument about string theory. That string theory has been around 30 years, and it still hasn't yielded any tangible connection with experiment. The multiverse people, one of the ways people believe you might be able to tell about the multiverse is that you might be able to see evidence of our, you know, pocket universe running into another pocket universe, and you might be able to see that imprinted in the cosmic microwave background radiation. At least that's what I've seen discussed. That's the clearest way that people have talked about it.
Good. I always thought that would be, I guess, as big a shock as that kind of discovery. I mean, so far there hasn't been whether it's space rocks or even Earth rocks. We haven't seen anything that's really outside the
Well, it's true that, I mean, that's the most amazing thing is that the entire universe that we look at, and we can look out back to 13.7 billion years, really does seem to obey the laws of physics that we can probe in our terrestrial laboratories. That's a remarkable thing that, you know, and that wasn't clear to people, that wasn't obvious to people when they sort of started this endeavor 100 years ago. So it does seem that every part of the visible universe somehow has the same physical laws. Now, if the multiverse is true, then another universe, right, one of these other universes that inflated from its own, you know, shred of space-time could quite likely have very different laws. And you wouldn't have rocks, perhaps, at all, or the rocks would have completely different properties. Yeah?
Do you know, or can it be proved that there's anything that can go faster than the speed of light?
You know, what's funny is those superluminal neutrinos that everybody was excited about. It looks like today, I think there was another experimental data yesterday was released that pretty much puts that out of the, most likely that's out of the ballpark. So it's not true. They actually, one of the things they found was a cable that was slightly off, and they actually could attribute the delay to a cable not being. And it's easy, you know, it's easy to laugh at this, right? But on the other hand, look, this is what science does. John Wheeler said, you know, the point of science is to make as many mistakes as fast as possible. So as long as these guys stood up and said, we were wrong, here's exactly how we were wrong, then they're heroes, right? They're not to be made fun of. They're heroes for doing it, because that is what science is all about. You know, that ability to make mistakes and then, you know, be clear about it. So as of right now, Einstein's still king. It's light. Yeah, back there. I'm not gonna be. Go ahead. You, yes. Ooh, you know, okay, thank you for asking that. So for people who don't know, so what she's asking about is quantum mechanics, right? So I said that there's gravity, and then there's quantum mechanics, and quantum mechanics is very weird. It's not just that the universe is broken up into little chunks, right? Quantum mechanics forces us to swallow, you know, there's a whole litany of strangeness about quantum mechanics. The double slit experiment, let me just sort of say briefly what it is. It's basically the idea that you can have two coexisting realities before an observation is made. You can have two coexisting realities that the world can be in this state of partial reality, right? So like there's this Schrodinger cat experiment or thought experiment. We have a cat in a box with a vial of poison. If a quantum mechanical event occurs, the vial will either be broken or not broken. And so before you open the box, the cat is in the state of it's dead and it's not dead, right? It's at the same time. Right? And of course you think that's impossible. The cat is either dead or it's not dead. No, quantum mechanics says it's both dead and not dead before you open the box, right? So this is like, you know, we could go on, I could do a whole lecture on this. So since quantum mechanics was founded 100 years ago, people have been asking, what the hell does that mean, right? And after 100 years, we still don't know, right? There are all these interpretations of quantum mechanics, one of which says, well, it's consciousness. You know, consciousness opens the box and somehow causes one reality to get chosen over another. There's another idea which says, when you open the box, the universe splits off into two, right? There's one where the cat is dead and one where the cat isn't dead. And then there's a whole bunch of other interpretations. And one thing I've written a little bit about this is that maybe, like I've had this whole lecture on cosmology, right? We're like, ooh, the birth of the universe, that's so cool. Maybe that's really the question. That's not the question we should be asking. We should be asking, what the hell does quantum mechanics mean, right? Our whole world is built on quantum mechanics, and after hundreds of years, we still have no idea what it's telling us. We can calculate and make things, but we still can't tell us what it means. So that's a preamble. My answer to your question is, I have no idea. Right? It's telling us something profound and powerful. Yeah.
I'll add to your mystery, and that is something that comes central to the issue of time. You can comment on it, but I'd like to hear you say something about the arrow of time.
Ah, the arrow of time. Yeah, right. Okay, so the question, the arrow of time, this is an old question. Why does time only go forward, right? Because the equations, the basic equations of physics, don't care whether you put plus t or minus t in it. In other words, imagine somebody showing you a movie of two billiard balls hitting each other, right? Could you tell whether or not the movie was being run forward or backward? No, right? You can't tell. For something like that, just two particles hitting each other. The equations of physics and the equations of quantum mechanics, too, are time direction independent. And yet, it's pretty clear that, you can't go backwards in time. The universe only moves in one direction of time, right? That's the arrow of time. And it is a fundamental mystery. And there seems to be something about when you get large collections of stuff together, not 2 atoms, but 1 trillion atoms, now, the arrow of time emerges out of their collective interactions. This is the laws of thermodynamics, right? So there's an arrow of time, which you can sort of prove via what's called Boltzmann's H theorem, that, large collections of material will actually sort themselves out in a way probabilistically that there's only one way, you can't unscramble an egg, okay? But even there's still people who look at that derivation and go, And then there's other arrows of time. Like, for example, the universe was actually born in a very, very, very low state of what's called entropy, right? Entropy is a measure of disorder, right? So the universe had to be in a low state of entropy because if it wasn't, there never could have been any evolution, right? We see that the universe is clearly evolving. But what we understand about physical systems is that once you get to what's called high states of entropy, things stop evolving. If I have a hot cup of coffee in a cold room, eventually the heat bleeds out, right? And the temperature in the coffee comes to the same level as the temperature in the room, right? That's a transition from low entropy to high entropy. The universe clearly must have been, the universe is still evolving. It's not at that final state, so it must have been low entropy. Why? It's far, if you were to reach into a bag and choose an initial state of the universe, you have an infinite number of high entropy possibilities and only a few low entropy possibilities. So the arrow of time is still a fundamental mystery. Yeah?
Because matter predominates in the universe, antimatter particles have opposite.
I don't think you can use, that whole antimatter-matter asymmetry is still sort of another question that physicists are trying to ask. But I don't think you'd be able to get out of the arrow of time with using antimatter.
Don't antiparticles have reverse arrows?
You can view interactions as the reverse part, but I don't think you'd still get away from the causal asymmetry, the fact that overall the universe, that you are moving towards your death and not towards your birth. That I don't think antimatter would be able to get you out of that. Any other? Okay. Good. Great. Oh, we have one less. Yes.
Speaking of cultural relativity, I was always fascinated by somebody like Galileo, who was trying to invent physics, and he didn't have a clock.
Right.
He couldn't measure any dynamic phenomenon, any accuracy.
So he used his pulse or he used the swinging of a, yeah, right.
Very accurate.
I know. Yeah.
And so, with the invention of time measurement, must have been very crucial to the invention of science.
It played as you watch, actually, it played an ever increasingly important role, such that, like now, right, the GPS on all your cell phones, right, requires atomic clocks being flown around on the satellites, right? So that measurement of time, that ever finer measurements of time became instrumental to being able to build something like GPS, which then became instrumental to changing the cultural context in which we live. When I go back and find my hotel, I'm going to be using the GPS, going, oh yeah, I got to turn over here, right? So there's this constant interplay between those two.
All right, well, we don't have any more questions, so thank
you
you
very
again for the wonderful
Thanks for your
presentation.
time today. I appreciate it.
Dr. Hogan, thank you for the introductions, and thanks for everybody for coming.